Okay, so thank you, Luke, and thank you, Jean-Maria, for organizing this. I think it's great to have a nice big meeting like this. It would be better, of course, in person, but hopefully this is the last such online meeting we have to suffer through. So today I'm going to talk to you about weighted estimates for the Bergman projection. And I'm going to confess to being nervous for this talk, largely because not because of the material, but because the audience, everyone knows and loves these objects and thinks about them all the time. And I feel a little foolish at times telling experts things that they likely know. So I'm going to ask the experts to bear with me as I tell things for people who maybe are not as much experts, and to kind of tell the full story, because I think the story is very pretty and it connects to all kinds of things. So we're going to tell the story in the case of the unit ball, where things are very explicit and I can draw pictures and I can write down nice formulas, and I'll tell you how this can be modified in other settings as it goes forward. So let me give the motivation here. So we're going to be working with the unit ball in Cn, so the set of points in Cn whose modulus is less than 1. And the main player we'll start with is the Bergman space. And so these are the set of functions that are holomorphic on the ball. And if I integrate over the ball with respect to the Lebesgue measure, this is finite. Okay, so this is the space we all know and love in various contexts. Now, we can all probably come up with proofs that say, if I look at point evaluation, this gives rise to a bounded linear functional. This largely follows from like the mean value property. And so from this, via the Riesz representation theorem, we know that we can recover the function by f against a certain inner product against a reproducing kernel. And here, kz of w will be the reproducing kernel for this Bergman space. And we know that it has the formula 1 over 1 minus z bar dot w to the dimension plus 1, where z bar dot w is the inner product between the vectors. Okay. So we also know that A2 of the space lives inside L2 of the space. Well, that's obvious because we just defined it with the norm and looked at the subspace. And so then we should have some orthogonal projection that goes from L2 of the space to A2 of the space. And this will be the Bergman projection that we all probably think about in many ways. And it works in the following way. Pf of z is integral over the ball, 1 over 1 minus z bar w to n plus 1. F of w dv of w. And so we know trivially, because this is the orthogonal projection, that it maps L2 to A2 bounded. And then the first question you might encounter as someone who's more motivated in harmonic analysis is, what does this do for LP? Is this still well behaved on LP? So the first question we encounter is, does P map LP of the ball to LP of the ball when P is in the reflexive range? Well, again, we all probably know the answer. So a reason to care for this is it helps us understand things about the dual space. If I want to understand the dual of these things, I should worry about the conjugate space. Okay. So the first answer to this question is very simple. We've actually heard it discussed, at least the proof idea discussed in other talks already today. So this is a theorem you can encounter. So the following are equivalent. So one says P maps LP of the ball to AP of the ball. Now I didn't define AP of the ball, but everyone I guess can obviously go through and do the global replace where 2 goes to P to make things work. The second condition is what we'll define as P plus of F of Z. So this is going to be integral over the ball. And you look at the absolute value of the kernel. And this operator maps LP to LP. And P is between 1 and infinity. So the thing that's nice about this theorem is it connects P, which has some singularity and some cancellation, potentially, with something that's always positive because I've taken the absolute value of the kernel. And then the proof of this is rather straightforward. So it's just 2 ingredients. One ingredient is the Rudin-Farrelly estimates. Which in this context say something like if you integrate over the ball and you have some expression of this type, this integral is like 1 minus mod z squared to the minus c. This is dv of w. And the second ingredient is the Schur test, or Schur lemma, maybe it's sometimes called. Since you can reduce to positive operators, then to understand the LP mapping properties for positive operators, you just need to check the following kind of inequalities. So you have some kernel, and you miraculously guess some function, then you need this to be no worse than, so here I integrate in the y variable, in here I integrate, in the other one I integrate in the x variable. Sorry, this should be x, y. And P is conjugate to Q. Okay, so I won't say more beyond that. The key point is that this thing here is your K of Z more or less for appropriate value of C, and you just feed that into this expression over here and then compute. Because your kernel is given by this expression right here. It's explicit kernel, it's positive. Okay, so that's question 1. And now what we want to do is get to the title in some sense. So I want to go to question 2. How does P behave on weighted spaces? And I'll define what I mean by this in a second. Okay, so again, let me just tell you the story for kind of P equals 2 because it's a little easier in certain contexts. So we're going to look at L2 on the ball with respect to some weight sigma. And so these would be the functions f such that if I integrate over the ball with respect to the absolute continuous measure sigma times dv, I get a finite quantity. Okay. And so the question we want to address is it the case that P, the Bergman projection we started with, does it map L2 of the ball with respect to sigma to L2 of the ball with respect to sigma. And we would like some test, some sort of necessary and sufficient condition on sigma for when this holds. So as an example, just going back through the sure test and the thing above, if you took sigma of z to be the standard radial weight on the ball, so this is, you could call it a standard weight, or if you're more familiar with the harmonic analysis literature, you might call this a power type weight. And so then you can show that P maps LP of sigma to LP of sigma if and only if -1 is less than T is less than P minus 1. And this just follows from using the Rudin-Farrelly estimates in Schur's testing. Now, this is a very special weight, and we'd like to be able to do this for all kind of reasonable weights. And this leads us to the kind of the motivating theorem here. And so this is a theorem due to David Becquelet, who was in the audience earlier. I don't know if he's still in the audience. And this is from 1981. And I'll paraphrase his theorem. So he did it for all P, but I'll also extract the stuff that we want for the moment. So P will map L2 of the ball with respect to sigma to L2 of the ball with respect to sigma, if and only if P plus, so remember the one where I take the absolute value of the kernel, so I've removed all the singularity on the kernel in some way. This also does the same. If and only if, and now this is going to be the test that comes about. And the test says that sigma belongs to a class we'll denote by B2. And these are now appropriately known as Becquelet Bonamy weights. And I won't tell you exactly what it is, but I'll tell you approximately what it is. So the condition you care about is you look at a soup over some geometric objects or some sort of collection of balls that are close to the boundary of the unit ball. And what you're going to do is you're going to look at the average over the ball of sigma times the average over the ball of sigma inverse. And these are with respect to dB. And you want, we'll denote this as some sort of characteristic and norm, and you want that soup to be finite, okay? So this gives us our test. This is our necessary and sufficient condition so that we can now verify when the Bergman projection is bounded on these weighted spaces. The test changes slightly if P is not 2. I'll leave it to I'll leave it to you to check out what it could be. It's not so difficult to figure out what it has to change to. There's a couple key facts I want to make here. This condition here that we're working with, for those who know these words, this is something akin to the Muckenhaupt AP condition. And so that's this is the analog of this concept in the Bergman space setting. So let me just make some remarks here. So the first remark you can show is that this characteristic is always bigger than 1. That's just Cauchy-Schwarz in some appropriate applied fashion. The other remark I will make is that the proof, as I've stated here, is qualitative. It gives you a necessary and sufficient conditions. At the time when this was done, there was not as much of a push to get quantitative statements. And so more recently in the harmonic analysis literature, there's been an enormous push to go back through and reprove certain theorems and track quantitative behavior. So once I know the function, the operator behaves on LP, I want to know how it depends as a function of P or a function of the parameters going into things. So this gives rise to the let me say how this was proved, and then we'll get to the next question. So the method of proof here was to use harmonic analysis ideas. So in particular, use the good lambda inequality. So use good lambda inequalities. Use connections to Calderon-Zygmunt theory, for those who know those words. Basically, the Bergman kernel becomes some sort of singular integral operator in an appropriate metric, and then you can appeal to the appropriate theory by which to study things. Okay, so once we have the qualitative theorem, we then decide to become greedy and go back and say, can we get a quantitative version? And so what we mean by that is we would like to understand the norm of this projection as a map from L2 of the ball with respect to sigma to L2 of the ball with respect to sigma. And we would like to show that it behaves as some sort of explicit function of this characteristic that we're working with, okay? And determine f of t explicitly. Okay, so turns out you can do this. Let me tell you the theorem that exists. So this was a theorem that was obtained with Edgar Chundia. He was visiting WashU as a Fulbright fellow for a year, and so we worked on this question when he was there, since this was in his area of expertise. It was also done with Robert Raum, who was my PhD student at the time. And this is from 2017, and it's in Math Z. And the theorem states something like this. So I'll go through and tell you a couple facts here. So first is saying that if you know this projection is bounded, then in fact you had to know that the weight belongs to this Bécquelet-Bonamy class. Okay, so this one here says B2 is necessary. Again, this was also observed in Bécquelet's original work, but it's just exact dependence was not tracked. Then you can replace this by P plus. So again, the kind of cancellation of the kernel does not really play a role. And then you can get the characteristic here to the power 1. And so this inequality says that B2 is sufficient. Okay, so let me make a remark here that this proof was inspired in many ways by a proof by Sandra Pott and Maria Cristina Reguera from 2013, a JFA paper, where they proved a related fact for the Bergman projection on the upper half plane. Okay, so they just did one variable, but upper half plane. And they achieved similar quantitative necessary and sufficient statements. Okay. So now I want to talk to you about the tools that go into this proof and describe them a little bit. And I won't go into amazing detail on it, But what I'll give you do is some sort of sketch or overview of the ideas. So I want to talk about kind of recent ideas in harmonic analysis as part of this. Okay. So let me write down an inequality, and then we'll explain how this inequality comes about. So the goal is to understand the Bergman projection. And we're going to take the absolute value of the Bergman projection because I'm trying to get norm estimates, and I might as well do so. Now, we know, because we can just bring the absolute value inside the integral of how it's defined, that this is dominated by p plus of the absolute value of the function itself. And so now what we want to do is we're going to dominate this by something, and I'll explain how this comes about. Okay, so let me write down what it is, and then I'll explain this inequality. So we're going to sum over L equals 1 to some function of the dimension. We're going to sum over alphas that belong to some collection, and then we're going to have some sort of averaging operation. And so here, if I write this expression, I mean 1 over the measure of E integral over E g dv. So I'm taking the average of the function with respect to the measure, and 1 sub k is the corresponding kind of indicator function on that set. Now I can't draw pictures in R in several variables well, so what I'll do is draw you a picture in the disk, and we have to kind of imagine how this works, and then I'll draw it on in kind of some sort of stretched out version that looks closer to the upper half plane. So here's the idea. Now you have the ball, and what you can do is you can decompose the ball into dyadic cells. Now, for those who are familiar with something like the Whitney decomposition, basically what you're doing is taking the Whitney decomposition of this object. And I'll draw the picture in, that you should kind of have in mind. So you take kind of the core of the domain, and that's the root, the very beginning of your construction. And then you look at, now if this were the circle, this is very easy, or the disk, this is very easy, because I have the whole circle, and then I can divide the circle into 2 halves, and each of those halves gives rise to something. So here would be kind of the corresponding first half, here would be the corresponding second half. And then each of those halves give rise to 2 other halves. And you continue that construction on and on and on. So if we were to draw it a slightly different way, and you were to zoom in, you can imagine here's the boundary. You have kind of a Carlson cube that comes about, and you take the top half of one of these cubes. So this shaded region here would correspond to kind of this region here. And then if I were to draw the corresponding 2 children that this thing has, that would correspond to those 2 children that I've just drawn there. And each of those has 2 children. Okay, everyone understand the picture I'm trying to go with? I can see a couple heads nodding, but I only see myself talking and a couple heads nodding, so I have to go with those heads and assume everyone else is with me. Okay, so on each, so I call one of these objects K alpha, okay? On each K alpha, we can estimate the kernel very well.
So,
and so
maybe
yes,
say something about this, but how are you gonna do this in several variables? So then.
Okay, so there's a couple ways you can do it. So the way I kind of talked about here in the case of the circle and the disk, I took the dyadic boxes that live on the circle, and then to each of those dyadic box, I take the corresponding Carless intent or Carless box, and I take the top half. Okay, and that gives rise to this kind of construction here, right? We're okay with that idea. Now it turns out that on the unit ball in CN, this is also a space of homogeneous type. And that means that there's a dyadic structure that exists on there. So there's a way to define open sets so that you have this kind of dyadic cube property where I have a cube and each cube has some children that have then children, and I can build the corresponding Carless intents in the same way. Is this?
Yeah, sure. So this is like the Korani. You're using the non-isotropic.
Yes, yes. Okay, so on each of these, we can estimate the kernel. And so we can say that something like, if I integrate over one of these boxes, this looks something like and put an absolute value so there's no problem. This looks something like the average over that cell times the corresponding indicator function, as long as I'm measuring on that cell, okay? So this just follows about because largely that the volume of one of these cells is basically the same as this appropriate radius to the power. Okay, so that's the geometric fact or the connection between the kernel and geometry that's somehow being exploited in this. Now, there's a slight problem in that I could choose 2 points, Z and W, which don't belong to the same dyadic box. So the idea could be maybe you say, well, here's where the point Z lives and here's where the point W lives. So they don't live in the same dyadic box. They're very close kind of Euclidean sense, but they're very far away in this dyadic structure I might have built. The idea then is you don't use the standard grid, but you rotate it slightly. So you take a rotation. If I were to shift this picture here by some amount to the left, then both of them would be in the same cell. And so it turns out that in fact, you can do this on a general space of homogeneous type. You can build these kind of random dyadic lattices so that you can have properties such as any cube or any ball can be comparable in an appropriate sense to one of the dyadic ones. So that's and phrased in that way, that's a result of Heitonen and Karema. Okay, so that then accounts for how this arises. So here in this expression, this term is kind of like the discretization of the integral P plus. You're adding up all the averages on each cell. And this term here is accounting for the fact that I might have cells where Z and W are somehow close, but not in the same cell, and I need to rotate things around a little bit. The key point is that this thing only depends upon some dimensional constant. It's some absolute term. And so as long as I can control these operators here in some universal way, I would then be okay because I just get some dimensional constant that I'm willing to track through the proof. Okay, it might be very large, but who cares? It's, you know, finite. Okay, so then the other, we kind of talked around it, but let me just say in words, use dyadic lattices on spaces of homogeneous type. To argue that any Bergman ball or Bergman cube in this setting is well approximated by dyadic ones. Okay, and so this uses harmonic analysis on spaces of homogeneous type. Okay, So what we've then reduced to we want to consider the following operation, which we'll call script S, acting on F. And what it's going to do is it's going to sum over all the elements. So I index each of those elements in the corresponding dyadic kind of lattice I build on the domain. So I have the core, and then I have the children coming off the core, and then the children's children, and the children's children's children, and so on. And what we're going to do is we're going to look at the average of F on one of these cubes times the indicator on the cube. And I want to show that the norm of this operator S as a map from L2 of, let me call it W now, to L2 of W. So I just changed the letters that I want to work with. I want to show that this is finite, okay? And in particular, I want to track the quantitative behavior. So now it turns out this has been a very recent fruitful line of investigation within harmonic analysis. So this is some sort of analog of something called a sparse operator in harmonic analysis. And it turns out that once you know things about these sparse operators, you basically know many, many things about all kinds of standard operators in harmonic analysis. So this is a good kind of simple replacement, dyadic replacement to work with. So this is equivalent to, this next statement is some sort of change of variable argument that you want to show that S acting on sigma dot as a map from L2 of sigma to L2 of sigma inverse is finite. And here you should think of sigma inverse as just W. Sorry, no, that's the same, we're okay. So let me tell you how you prove this last box, okay? This last box is what's gonna easily give rise to this Bécquelet-Bonamy type constant. So what we do is we're left with understanding some sort of behavior like this. And so we write this as the sum over alpha in here alpha G sigma inverse indicator K alpha okay. So let me write out what happens here, and I'll try to collect the terms. So I'm going to leave some gaps, and so that way you can say there's a gap in my proof, and then we'll fill the gap as the thing goes on. So what we're going to do is I'm going to write a sigma of K alpha in, and I'm going to divide by a volume of K alpha, and I'm going to put a 1 over sigma of K alpha. And then I'm going to have an integral of F dV. So this term here is exactly this term here. I just multiply and divide, use definitions, and see what it is. We're going to do the same with this expression here. And if we do that, for the other term, you get something that looks like sigma inverse of K alpha times 1 over sigma inverse of K alpha, an integral over K alpha, G sigma inverse dV. And then I'm going to divide by a volume of K alpha, and I'm going to multiply by a volume of K alpha. And that corresponds to this other term that we had. I don't know, people can maybe not see red. We'll see. I apologize to those who are colorblind if you don't see the red. Okay, now let me box a couple terms. So these terms here, this is the B2 condition. This is the thing we can control by B2. All these other terms, you have a function with respect to some measure divided by the measure of the set. And so for those things, you can control by a maximal function. So this thing looks then like this B2 condition you want times some sort of integral of a maximal function of f relative to sigma times a maximal function of sigma inverse applied to G dV. And now what you do is you do the standard trick where you multiply and divide by the appropriate weight. And so this then becomes the characteristic you're after, the norm of the maximal function in L2 of sigma, the norm of the maximal function in G for L2 of sigma inverse. And the miraculous thing that holds is that these maximal functions are somehow universal relative to the weight. So as long as the weights behave well, the maximal functions map the weighted LP space to the weighted LP space. So in the sense that this weight and this weight are behaving nicely. So this gives me sigma D2 times the norm of F in L2 of sigma times the norm of G in L2 of sigma inverse. So if you track through this whole proof, what we have is that the norm of this sparse operator as a map from L2 of sigma to L2 of sigma is no worse than this constant. And that's good. That says each sparse term is bounded, and I have some finite number of them, so each of them are bounded, and so that's the answer. Let me give you a couple corollaries you can get from this. So the first corollary is that maybe you want to know how P and P plus as a map from LP to LP behave as a function of P. You can show that this behaves like P squared over P minus 1. And the way you can do that is just test the corresponding behavior of the appropriate weights to figure this out. The other corollary you can get from this is that P maps L1 on the ball to weak L1 on the ball. And in particular, this says that if you look at the measure of the set where PF is big, this is at most a constant times 1 over lambda times the norm of F in L1. Okay, so in the last 10 minutes, I want to tell you some other places we can do this. So these are the rough ideas that go into it, and I want to tell you where it can be used elsewhere. So the general ideas work in other settings. So let me just say a few words about one of them. So the first one is more general domains in several complex variables. The terminology that I believe I've seen, these are sometimes called nice domains in the sense of McNeil. And so things that fall into this are domains of finite type, in C2, C infinity, strictly pseudoconvex domains, in CN, convex domains of finite type, in Cn, and decoupled domains of finite type. In Cn. And so the theorem you're able to prove, and this was obtained with Zhenghui Huo, Nathan Wagner. So Zhenghui was a postdoc at WashU for a period of time, and Nathan is a current PhD student there. And these have now been appeared or accepted in respectively 20 and 21. So let me just first say there's a quantitative qualitative is what I want to say first. So there's a qualitative version for nice domains, and this is in the journal Geometric Analysis from 2020. And then there's a quantitative version in the Bulletin Sciences Mathématiques from 2021. It's of the exact same flavor as what I said for the unit ball. So the proof is largely the same. You have to build an appropriate dyadic structure on these objects. You have to then show that these kernels behave well. So in the sense that the estimates on the kernel are somehow comparable to the volume of the corresponding dyadic cells you build. And that's where, because we know very good information, based on lots of excellent research, we know all these domains have very explicit kernels with good estimates. And you can get the similar corollary. So we know the Bergman projection is weak type bounded. We know the quantitative behavior as p goes to infinity, and so on. Let me give another example. So there's something called matrix weighted questions. Matrix weighted Bergman spaces. And let me just say here, we can prove similar theorems. But I don't want to tell you what those theorems are, because if I do that, I take away from the person who speaks after me, and he'll be irritated. So let me just encourage you to stick around for Zhenghui's talk, where he'll talk about what these theorems are and how we prove them. So. And the last one we were able to do things is the Hartog's triangle, which again played a role. Again, it's because we can connect things very explicitly to the Bergman kernel and the corresponding structure. So this appeared in the very first talk of the morning. So I look at the points Z1 and Z2 in C2 such that Z1 is less than Z2 is less than 1. And then there's a theorem due to Zhenghui Huo and myself that appears in the Journal of Functional Analysis, I think from 2020. That says for a certain class of weights, and so let me just put it in quotes here because there's not time to write it all out. Quantitative information about the Bergman projection. In weighted LP spaces on the Hartog's triangle. once you have this quantitative information, you can get at some prior work due to Eunice Setunsu, Debraj Chakrabarti, Liwei Chen, Jeff McNeil, and Luke Edholm that studied the behavior of these spaces on LP. So you can recover prior work about LP regularity. For the corresponding Bergman projection on the Hartog's triangle. The thing that I found so interesting about this is that I guess, as many of you know, the restricted range, this Bergman projection is not bounded for all LP like we all like it to be. It's only bounded for some restricted range, and the conjugate exponents play a role. There's even corollaries for these fattened Hartog's triangles, and you can write down the corresponding theorems that might come about. There's some restricted range of P's where you're able to come up with things. So I'm going to go ahead and stop there.